Tuesday they're going to be 10 to 12:30. I don't know, I think last time I said 9. But, and then Thursday, that's still 8 to 11. So this is the 5th, and this is the 7th. This is dead days. If you want to come during dead days, you can do your exam. That'll be the only dead days. Okay, so, and then your final is Tuesday, May 12th. I don't know what test is. 1:15 to 3:15, it sounds like. And it's in here, that's the other thing. Your exam form is in the testing center, but the final is in here. Okay? Also make sure that you're here a few minutes early for the final, because there's a seating chart. Okay? Each row is actually labeled with a letter, and each seat is actually numbered, so you'll have a assigned seat when you come in that day. And bring Scantron 882 to the final. Okay? And I told you there'll be 64 questions, 16 to represent each exam. Now this test will only have, I've already written it, will only have 36 questions because there were only 3 chapters, so it's a little bit shorter than your other exams that we've had, so 35 plus 1 extra credit. Okay? I will also say this exam has a lot of control on it. Okay? Because not only was there control in chapter 18, but there was also control in chapter 21 as well. Okay? So there's quite a bit of control on it. Okay. Let's go ahead, we'll go through the review and then we'll do the practice test. The practice test is kind of a piece together practice test because in the past we've covered chapter 22, which was photosynthesis, and since we didn't have that, I kind of had a piece of practice test together. Okay, so for chapter 18, you need to know the 3 steps for making glycogen. And you know that the precursor is glycogenin, because you can't just put 2 glucose molecules together. You actually need the precursor, which is glycogenin, which actually is its own enzyme, and does put the first, I think it was 6 glucose molecules together. And then from there, glycogen synthase will take over from there. So you should know the 3 steps for glycogen synthesis. The control, which is the main point there, is going to be glycogen synthase. Okay, so just like on your worksheet, and you have 2 parts to that. You have 2 forms of that: glycogen synthase I and glycogen synthase D. Glycogen synthase I, which was on your quiz, is dephosphorylated and is the active form, glycogen synthase I. And then glycogen synthase D is the inactive form and it's phosphorylated. Okay? Glycogen breakdown. Oh, the other thing too that was on your worksheet, I had a mistake on the worksheet for chapter 18 and I fixed it and I reposted it. So it was just, I talked about allosteric control for glycogen synthase, but I listed the same thing twice. So I fixed it though. It's ATP and AMP. Okay? So for glycogen synthase, ATP is going to be a positive allosteric effector. AMP would be a negative allosteric effector. Okay, so I did make a correction on the worksheet and I reposted it. Okay, a glycogen, and you also need to know all of the glucagon, epinephrine, and insulin. But I actually am going to take a little bit of time and I'll write them on the board and we'll say what processes they activate and which ones they inhibit. Okay, so right now we're not going to go over that at the end. Okay, so the glycogen breakdown, you should also know the 3 steps for glycogen breakdown, but again, the control step and the important step there is going to be glycogen phosphorylase. Okay, and you have forms A and B. And form A is going to be the active form, and that is going to be when it is phosphorylated. And then B is the less active form, and that's dephosphorylated. And then you also have allosteric effectors for that too. This is all stuff that was on the worksheet. So if you did the worksheet, then you should already have most of this. Allosteric effectors were a little bit different for this one. This was going to be that for breaking down glycogen, you had ATP, glucose, glucose 6-phosphate, caffeine. All of those were going to be negative allosteric effectors. But AMP was a positive allosteric effector. Yes?
I'm just curious why caffeine.
You know, I actually don't know the answer to that too. It's something I need to look up because I was wondering the same thing myself. Why is this on there? And so I'm going to have to look that up to see. I don't know the answer to that. I would like to know that because I love Diet Pepsi, so. Okay, so you should know, again, control of glycogen synthesis and glycogen breakdown, but we'll take some time and we'll do a little bit of that on board. Gluconeogenesis, you should, again, a lot of this is off that worksheet. So gluconeogenesis, what are the 3 steps that are different in gluconeogenesis and in glycolysis? Because it is the reverse of glycolysis, but there are 3 steps, actually the 3 control steps of glycolysis that we have to get around. Okay, so those were 1, 3, and 10, which were, like I said, on your worksheet. And you should know, of course, the enzymes that are going to be involved with that as well. The main enzyme in terms of control, though, for gluconeogenesis is going to be the fructose 1,6-bisphosphatase. Okay, that's going to be the main control one for gluconeogenesis. Okay, and then of course, we talked about fructose 2,6-bisphosphate. Now this one, again, like I said, I want you to know big picture with glucagon, epinephrine, and insulin. But then this one you should also know too. What happens? Oh yes, question in the back.
Sorry, did you say the control for gluconeogenesis was fructose 1,6 or 2,6?
No, it's both really, but the actual enzyme involved in gluconeogenesis is fructose 1,6-bisphosphatase.
Okay.
Yes. Then you have this control substance, which is this fructose 2,6-bisphosphate, and it's controlled, of course, we talked about that, by phosphofructokinase 2 and fructose phosphatase 2. So that's why that gets used with that. So anyway, you should know what happens if we're making fructose 2,6-bisphosphate and if we break it down. And we did all this on the board before as well, but if it gets made, what happens is it's going to turn on glycolysis, and it turns off gluconeogenesis. Again, this is actually a question on the worksheet, okay? So if we have it, if it's made, okay, it turns on glycolysis, turns off gluconeogenesis. If we break it down, and when you break it down, you break it down into fructose 6-phosphate. So if it gets broken down to fructose 6-phosphate, what happens then is now we're not stimulating glycolysis, so we're basically, no, not inhibiting, but we're basically decreasing glycolysis is probably a better way to say it. And then it allows or turns on gluconeogenesis. Okay? And remember, there were 2 enzymes that controlled that. I probably am not going to ask you any questions about this, but we had that if you have phosphofructokinase 1, well, let's just do the abbreviation. Okay? When it is dephosphorylated, then we get this is going to be the active form, and it's going to make this. Okay? But then we also have fructose bisphosphatase 2, and when it is going to be phosphorylated, it gets turned on, which then breaks down, and we get fructose 6-phosphate, which turns down glycolysis and turns on gluconeogenesis. So those were the 2 control enzymes. I told you these 2 control enzymes are actually one enzyme with 2 active sites. So that when it gets phosphorylated, it basically turns this one off, turns this one on. When it's dephosphorylated, it turns this side on and turns that side off. So it's a good way of controlling both at the same time. Okay? But I mainly, big picture, just like on the worksheet, what happens if we make this? What happens if we break it down to fructose 6-phosphate? Okay. The Cori cycle, you should know that the Cori cycle is used basically as a recycling process. The Cori cycle then allows us to take the lactate that we were making. Remember, the lactate's an endpoint in the muscle, but then you have the Cori cycle, which is occurring in the liver, and you can now recycle that lactate back to glucose using gluconeogenesis.
Wait, can you do that?
Sure, the Cori cycle, remember that lactate is going to be, or lactic acid is going to be the endpoint in the muscle. We take pyruvate, and if we're under anaerobic conditions, it's going to be converted to lactic acid or lactate. That's an endpoint. But if you take it back to the liver, you can recycle it, and it can be converted back to glucose using gluconeogenesis. That's the Porte cycle. It's just a process of doing that.
It takes it back to the remains.
Well, if it's glucose, then it goes back to the bloodstream and it can go wherever it needs to be used. And then the pentose phosphate pathway. I told you you didn't really have to know the pentose phosphate pathway. I just wanted you to know what was its use. And remember, its main goal, it still uses glucose, actually uses glucose 6-phosphate, but it doesn't make ATP, it's going to make nucleic acids. And it also uses its coenzyme is NADP. But that's all I really wanted you to know. I didn't want you to know the steps or the pathway. You just had to know what is it used for. Yes?
Did we talk about hormonal control?
No, I'm going to write it on the board. That's why I skipped it. Okay, so let's go ahead then, and let's write them on the board, all the little things on the board. Yeah, it's gonna take me a minute. I'm gonna make a chart. Talk amongst yourselves. Okay, so there's all the different pathways we've talked about so far and the different controls. So insulin, and I definitely want you to know the big picture for all of these. There will definitely be a lot of questions on the test about this, so you want to make sure you get this down. But honestly, you can think through this logically, okay? So if we have high blood glucose levels, basically our goal is we're needing to get that glucose out of the bloodstream. So anything that's going to use glucose would be turned on. Okay, so glycolysis will be turned on. Gluconeogenesis is going to be turned off, or you could say inhibit or activate, whatever words you want to use, because the whole goal of gluconeogenesis is to make more glucose or make more sugar. Well, we don't want to do that if we already have high blood glucose levels. And then glycogen synthesis, that's going to be turned on, because let's take the excess glucose and let's go ahead and store it as glycogen. Glycogen breakdown, that's going to be turned off, because the whole point of glycogen breakdown is to get more glucose. Well, we already have enough. We have high blood glucose levels. Beta oxidation, that's going to be to break down fats as energy. Well, that's going to be turned off, because if I have high blood glucose, our body or animals want to use glucose as their primary source of energy. So if we already have high blood glucose, we don't need to break down fat for energy. We'll use the glucose for that. But it will turn on fatty acid synthesis, because then what do we do with those excess fatty acids or excess acetyl-CoA that we get? We'll make them into fats and store them as fat. Okay? So again, logically, you should be able to walk yourself through all of these. Then glucagon. Glucagon's released when you have low blood sugar levels, like you've gone a long time and haven't had a meal. That's going to turn glycolysis off because we don't want to take the little glucose that we have and send it through glycolysis. That's using up more. It's going to turn gluconeogenesis on because the point of gluconeogenesis is to make more sugar. To make more glucose. Okay, it's glycogen synthesis. It's going to turn that off because we don't want to take the little glucose we have and store it as glycogen. We need it. And it's going to turn glycogen breakdown on because breaking down glycogen, the whole goal of that is to get more glucose. Okay, and then beta oxidation, it's going to turn that on. And the reason why it turns this on now, though, is we have low blood glucose levels. When we have low glucose levels, we need energy still. We're going to get that energy from fatty acids. Okay, so we'll turn that on. And then it's going to turn this off because, again, we don't want to waste energy making fats or taking that acetyl-CoA to use it to make fats when we can use that as energy. Okay? Okay. And then epinephrine is a little bit different, though, because epinephrine is not related to glucose. It's related to fight or flight. You've seen a bear, and you are running from that bear. So the goal here is we need energy. That's the whole goal. So it's going to turn on glycolysis because it's going to help us make more energy. It's going to turn off gluconeogenesis because, if you remember, gluconeogenesis takes 6 ATP to make 1 glucose. That's actually using energy. It's also going to turn glycogen synthesis off because we don't want to store our glucose as glycogen. We want to use our glucose for energy. It's going to turn glycogen breakdown on because if we break down glycogen, we can get more glucose, which will lead to more energy. And then beta oxidation, it's going to turn that on because, sure, let's break down fats and use some energy there too, depending on how long we're running. If we're running short distance, we may not get to that point, but, and it's going to turn off fatty acid synthesis because, again, that takes energy to make fats. And right now, we need all of our energy because we're running from a bear. Okay? Yes?
I had a question about epinephrine and gluconeogenesis. So even though you invest 6 ATP to make the glucose, wouldn't you get more ATP after?
It would honestly depend what's happening with your blood glucose levels as well. It would depend if we were low on our blood glucose levels, and that might be worth that to do that. It also depends on, normally your fight or flight response is like an immediate response. So it's more likely that we're just going through glycolysis, not necessarily a citric acid cycle electron transport chain. We need fast energy. So it depends. I mean, how long are you going to run from the bear? I don't know. If it turns into miles that you're running, then that might come into play. But initially, it's just anaerobic respiration without oxygen, so it's just glycolysis. Okay, so you definitely should know these. Now, you can replace those terms because on the test, instead of saying on and off, I'll use activate or inhibit. So you can replace those terms with activate or inhibit. Okay? Okay, so that is chapter 8 with a little bit of chapter 21 thrown in there. Okay, so the other thing too that you should know, and it was like I said on the worksheet, is how does ATP and AMP play into these as well? Okay, ATP and AMP, because they're pretty much allosteric effectors for all of these processes as well. Okay. Okay. Chapter 8. I'll tell you there's, in terms of proportions on this test, there is the least amount from chapter 8. Okay, so a very small percentage from chapter 8 is on this test. Because chapter 8 is just hopefully a review for most of you if you've taken any kind of biology course. Okay? As you saw in the practice test, very similar, or as you saw in the quiz, I'll definitely ask you about the structure of a fatty acid. So I'll probably give you a fatty acid, not probably, I gave you a type of fat and you have to label that fat. Okay? And so just like on the review, I posted a review sheet for chapter 8 as well, and it basically just wants you to give structural features so that you can figure out what kind of fat you have when given one. Okay? So similar to that. Yes?
On that, the only one that I'm wondering about recognizing the sphingolipid, the sphingosine backbone.
I'm going to make it very easy because I will just use one of the pictures from your slide if I decide to use that. Because if you do Google it, they actually have very different structures, and so it may be harder to see the glycerol, to see the sphingosine backbone, but it'll be very similar if I decide to use that one like the slides, so that you can very easily see the 4 carbon member backbone. Okay. So then characteristics of lipid, you should know what saturation means, and of course for a fatty acid, saturation means that there are no double bonds. right? We're saturated with hydrogen, is how you can think of it. Okay, and of course then unsaturated means there are double bonds. And remember that we talked about the abbreviated way of writing that, that if you had something that was 8, you saw it on the quiz, if you had something that was 18 carbons, you would list it like this if it was 18 but it had 1 double bond, and then you would do a triangle and you would say where those double bonds are. Okay, so this would indicate that's 18 carbons long, there's 1 double bond, it's at position 9, or carbon 9. Okay, so you should know that terminology. Okay. You should also know the term amphipathic. We've seen that before, yeah.
Just regarding that, the temperature, if it's,
The melting point?
yes.
Okay, so 2 things affect the melting point. I'm not sure if I have it on there or not. But 2 things affect the melting point, and that's going, or transition temperature. Transition temperature refers to a cell membrane, and melting point just refers to the fatty acid by itself. So melting point for the fatty acid, 2 things are going to affect it, and that's going to be the size. So basically like its molar mass, how many carbons are there, okay? And the more carbons that are there, the higher the melting point. And then the number of double bonds. And the more double bonds you have, the lower the melting point. Double bonds actually cause the fatty acids to have to separate more, which makes it easier for them to go into the liquid form. Those 2 things, double bonds and the carbon length, really. Which that really does go into the transition temperature, yeah? Yeah, so transition temperature, again, just refers to the cell membrane. And this is maybe a little bit different. For the cell membrane, it talks more maybe about, for the transition temperature, it talks more about rigidity versus fluidity. So if it's more fluid, okay, versus if it's more rigid, and what affects that, there was a question on the practice test. What's going to affect that is going to be, again, the saturation of the fatty acid chains. Okay, so if it's saturated, meaning no double bonds on the fatty acid, that's going to increase rigidity. Okay, and then cholesterol will also increase rigidity as well. So those 2 things. I feel like one of these is actually playing.
Something's playing.
Something is playing. I don't know if one of you left it. Double check it, but instead of recording, I believe it's playing something. Because I keep hearing like another sound or an echo or something. But anyway, okay. So the biological membranes, this was also on that review sheet. And again, I sent an email out that said I posted answers to all 3 review sheets, so you have those. But the main components of membranes are going to be phospholipids and, okay. Ella, I think it's yours. I think yours is playing something instead of recording. So I don't know if you want to check it. Okay, so phospholipids, proteins, and cholesterol. And for the proteins, you should know there were 2 kinds of proteins, an integral membrane protein and a peripheral protein. And the integral membrane protein is one that spans the membrane. Those can form channels. And then the peripheral protein is normally attached to the outside of the membrane or inside of the membrane. Yes?
I know we did some review sheets, so looking at the different types of proteins was kind of one part, and then talking about the function of the protein as a part of the bilayer.
Right.
Is that?
Sure, and so for the ones that span the membrane, obviously those would be the ones that form the channel. The peripheral proteins aren't a channel, but they both can take signals from hormones, and they both can be enzymes, whether they're peripheral or integral. And we saw an example of an integral membrane protein being an enzyme with the electron transport chain. Each one of those complexes were actually giant protein complexes that were both span the membrane, and they were also enzymatic as well. We also saw them forming a channel with the ATP synthase. The ATP synthase, the F1, was an integral membrane protein, which allowed hydrogens to flow back in to make ATP. And then cholesterol, we said, was also in there as well as one of the main things, and that's going to, of course, increase the fluidity, increase the rigidity of the membrane.
So we only need to know for animals, not for plants?
Yes, just plants. Yeah, sorry, plant science. And then transport across the membrane, we talked about basically 4, but if you count primary and secondary active transport. But you should know basically 3 things about each gas.
Are cholesterol increases or decreases fluidity?
It will decrease fluidity, increase rigidity. Okay, so for each kind of transport, you should know 3 things about it. So simple diffusion, what you should know is that it's going with the concentration gradient, meaning going from an area of high to an area of low till equilibrium is reached. And because it's doing that, that's a favorable process, so no energy is needed. Okay? And then with simple diffusion, it's normally moving small and non-polar material. And because it's moving small and non-polar material, there is no protein carrier needed or protein channel needed.
Wait, small non-polar?
Small non-polar. We had the exceptions though of water because water goes through osmosis. I don't know, that was actually 4 things. I just mentioned 4 things. With the concentration gradient, no ATP needed, small non-polar, and no protein needed. So 4 things. Facilitated diffusion. Now this can be something that's larger and polar, so it's going to need a protein carrier or a protein channel to go through. Because remember, the interior of the membrane is nonpolar. So in order for something polar or large to pass through, it is going to need a protein.
But still no energy
But it,
going with the...
correct, but it's going to be going with its concentration gradient, so no energy is needed, yes.
So are simple facilitated diffusion both considered passive transport? or-
Yes.
Okay.
Passive transport meaning no energy needed. And in active transport, we had 2 kinds. We had primary and secondary. That they both are going to need energy because we're moving against a concentration gradient. We're going from an area that already has a low concentration to an area that has already a high concentration. So we're going to need energy, and then there is a protein involved because normally this is polar or large material as well that's going through active transport. And then the difference between active and primary and secondary active transport was just that primary is going to use ATP directly. We use the sodium potassium pump as an example. And then with secondary active transport, it doesn't actually use it directly. Something is flowing through with its concentration gradient that allows the substance to flow through with it, but at some point energy was used to create the existing concentration gradient. So it's not going to use, secondary is not going to use ATP directly. But at some point ATP was used. And then the last thing we talked about was receptor-mediated endocytosis. And that was with, we used the example of LDL. Yes?
I'm sorry, back to active transport, it doesn't need a protein carrier?
It does.
It does. Because it's moving around.
And then endocytosis was, and we used the example of receptor-mediated endocytosis, which was LDL binds to receptor. When that happens, basically a vesicle is pinched off into the cell. And that is normally for very large material. Or if control is needed, like with the receptor. Okay, so that's chapter 8. And again, like I said, less questions are from chapter 8 on the test than the other chapters. Okay, and then chapter 21, and it does start off right with the hormones, but I already did explain the hormones there in our little chart. Okay, how they control either fatty acid synthesis or beta oxidation, and beta oxidation is the same thing as breaking down fat. Okay, so we should know a couple things. We should know that first of all, the fatty acid has to be activated, and when that occurs, you're going to use what's equivalent to 2 ATP. Right, so we're taking ATP and going to AMP. Okay, and then we should also know that the fatty acid can enter into the outer membrane, but it needs the carnitine shuttle to shuttle it into from the inner membrane space into the matrix. Which answers another thing on here, which is where does beta oxidation take place? It takes place in the matrix of the mitochondria. That is also something I like to ask on exams. Where is the location of everything taking place? Okay, so you should know location. And this is going back to the last test. You should know where glycolysis takes place, where the citric acid cycle takes place, where the electron transport chain takes place. You should know where all of those take place.
Also, for glucogene,
There's 3 places.
there's 3, right? And that was the cytosol, the
Matrix of mitochondria and ER. Correct.
You said it, that for the fatty acid, enter into the outer membrane.
So you know that the mitochondria has 2 membranes, the outer membrane and inner membrane. It can enter freely through the outer membrane, but then needs a carnitine shuttle to move past the inner membrane into the matrix.
That's fatty acid.
This is for fatty acids. Because right now we're basically talking about beta oxidation. So then you should know the 4 steps of beta oxidation. You should know them both as like just what's happening, okay, like oxidation, hydration, oxidation, cleavage. You should know that. You should know the enzymes involved. You should know the coenzymes, and especially the coenzymes, because that actually results in energy, and we need to be able to keep track of our energy. And then I absolutely, just like you saw in the practice test, I'm going to ask you about a even numbered saturated fat, and you have to calculate energy, an odd numbered saturated fat, and an unsaturated fat. Okay? So you should know how to do the calculation for each one. We walked through them, and we did all of them. Again, hints I gave you was that for however many acetyl-CoA you get, it's going to go through the citric acid cycle. Every round of the citric acid cycle makes 10 ATP. So you'll take however many acetyl-CoAs that you get, you multiply by 10. For beta oxidation, for every round of beta oxidation, you make 4 ATP. So you figure out how many rounds of beta oxidation you're going to go through, and you multiply by 4.
Okay, is that for the unsaturated?
This would be for whatever you have, and then there's alterations we make for
I
unsaturated.
forgot what the unsaturated was, because saturated with even and odd, I understood. The
Saturated, yeah, so if it's unsaturated, you still, what I suggested you do is you still go ahead and do the calculation exactly how you would do it for just so, I
right,
think.
you add 4, right?
No, that's for if you have an odd number, yes. If it's unsaturated, all that's really happening, in terms of energy, you shouldn't say that. In terms of energy, all that's really happening is for every double bond, you skip step 1 of beta oxidation. And so you subtract out 1.5 ATP. Yes.
I have a quick question on the odd numbered ones. You subtracted 3 carbons,
Right, from the very
and then
beginning.
you had the same number of beta oxidation. Like if you had 15, you subtracted the 12, and then it's 6 and 6.
Right, because if we think, so if we think about it, if we subtract out that leaves us with 12. Now, what actually is going to really happen with this is in that last round, I'll have 5. I'll have a fatty acid that's 5 carbons long. And in that last round, it'll break up into 1 acetyl-CoA and 1 propanyl-CoA. And so I'm basically representing that right there. And so I can just go ahead and say, and take whatever's left over, and I can just divide that by 2, and that'll tell me how many rounds of beta
That's why you
oxidation.
don't get the extra acetyl-CoA.
Right. And so then, then all we get, if we divide by 2, we'll end up getting 6 acetyl-CoA and 6 rounds of beta oxidation.
And then by the end of that, you're going to add 4, right?
And then you need to add 4
Only
because,
really 2.
what's that?
Only really 2 that get subtracted.
Only really 2 what?
Well, you get 4, but you have to subtract 2 for the primary steps.
No, so what happens with the propanyl-CoA is propanyl-CoA will produce 5 ATP, but you subtract 1 because you needed to actually, as it went from propanyl-CoA to succinyl-CoA, you actually had to use 1 ATP, and so you'll subtract 1, which gives you 4, but that's it. Because in terms of the fatty acid chain, we'll subtract 2 at the very end for the activation, but that represents the whole fatty acid chain. So when we have 1 propanyl-CoA that results with this 3, you can add in 4 ATP net. Okay, so I did explain, yes, question back.
So what's the difference between the 3 methods? Like, what are their similarities?
Sure. If you have, so we can go through that. I'm going to erase this. We're all good with this one? Yeah? Okay. If we have a just even numbered saturated fat, Even numbered saturated. That's the easiest one because it has no other things we have to do. All you have to do is count how many rounds of beta oxidation. Rounds of beta oxidation. I hate telling you all these little sheets because you really should know what's happening. Okay, so how many rounds of beta oxidation and how many acetyl-CoA? Now, for the acetyl-CoA, it's very easy because however many carbons there are, the number of carbons divided by 2. That'll tell you how many acetyl-CoA you get. Okay? Now for beta oxidation though, you would take the number of carbons and you still divide by 2, but you subtract 1. Because even though it would seem like if I have 12 carbons that I would go through 6 rounds of beta oxidation, that's not true because in the last round there's 4 and they'll make 2 acetyl-CoAs in the last round. So we're actually not going to have 6 rounds of beta oxidation. So like I said, then however many rounds of beta oxidation you get, you multiply by 4 because in step 1 we make FADH2, which is 1.5 ATP. And in step 3, we make NADH, which is 2.5 ATP. So we add those together, and that's 4 ATP for every round of beta oxidation. Then, for acetyl-CoA, we're going to multiply by 10. Because if you walk yourself through citric acid cycle, we make 3 NADH, which is 7.5 ATP. We make 1 GTP and 1 FADH2, which adds up to 10 ATP made for every round of the citric acid cycle. And so if you're doing this one, all you have to do after this is add them together and subtract 2. Everything is going to have subtract 2 from it because you had that activation step. The activation step was to activate the fatty acid and it used 2 ATP equivalents. Yes?
Are you going to go over the odd number?
Yes.
And this is for unsaturated or saturated?
This would be saturated, meaning no double bonds. So this is an even numbered saturated fat. No double bonds in it. Okay. Then, if we had an odd numbered, what I suggested that you do, I need to really use an example, otherwise I can't do this. What I suggest that you do is you take the number of carbons and you go ahead and subtract out, at the end you're going to end up with a bunch of acetyl-CoAs and 1 propanyl-CoA. And the propanyl-CoA is 3 carbons long. So go ahead and just subtract that out right now, and that represents your propanyl-CoA. Okay? And then that would leave us with 12. Now when you get this though, when it's an odd numbered, after you subtract out the propanyl-CoA, you take the number of carbons, in this case 12, and you divide by 2. When you divide by 2, that tells you both the number of acetyl-CoA and the number of beta oxidation rounds. And then for the acetyl-CoA, you multiply by 10. For the rounds of beta oxidation, you multiply by 4. And then what you'll do is you'll add in 4 ATP, that's for the propanyl-CoA. Okay? And there was a step-by-step process for that. What happens is you end up using 1 ATP, you make it into succinyl-CoA. Succinyl-CoA goes in at the product of step 4 of the citric acid cycle. Since it goes in as a product of step 4, what you have left is step 5, 1 GTP, step 6, 1 FADH2, which is 1.5 ATP, and step 8, which is 2.5 ATP, to give you a total of 5 ATP. But to get from propanyl-CoA to succinyl-CoA, you used 1 ATP to give us a total of 4 for that 1 propanyl-CoA. But you have to remember too, you have to subtract out 2 for the activation step. So again, we'll be subtracting out 2 every single time for that activation step.
So after you add 4, you subtract 2.
You can subtract 2 whenever you want to, but you have to make sure you subtract 2 for the activation of the fatty acid. I'm just giving you a list of how I do it, but you can do it in any order you want to do it.
So you add 4 and then you get the total and then subtract 2.
That's normally what I do. I
Why
figure
don't
out.
you just add 2?
You can do that. Whatever works for you. This is my system. Okay. And then lastly, which is the easiest one, I mean the easiest exception here, is if you have an unsaturated fatty acid. The unsaturated means there's a double bond somewhere, okay? We talked about the fact that it does depend where that double bond is, because we need that double bond to line up at the alpha, between the alpha and the beta carbon, okay, on our fatty acid. But there's an isomerase enzyme that can move it if it's not exactly where we have it, and it doesn't actually use any energy to do that. So the only energy source that's going to be different here is the fact that you already have a double bond, and that basically skips step 1 of beta oxidation. So for every double bond that you have, you figure it out just like you would any one of these. You figured out the way you would. But then for every double bond, after you've done your calculations, you subtract 1.5 ATP, because you skip step 1 of beta oxidation anytime there is a double bond. So you do your calculations just like you do them if it was odd numbered or if it was even numbered, depending on what it is. And then for every double bond, you subtract out 1.5 ATP.
How would you show that on a test? Would you give the abbreviation of the saturated?
I could do either one. I could give you the name of a fatty acid and tell you that this fatty acid, because I've done it both ways. I can give you the name of fatty acid and I'll tell you that the fatty acid is 16 carbons long with 2 double bonds or something. But then I could also give you the abbreviated form, and you have to know what that means to do the calculation.
So if it did have 2 double bonds,
So-
you would 2 times 1.5 and then subtract it from the
Correct.
total that you got?
Like that. If it was written like that, then you'd do the calculations for 18, but then you would subtract out 3 ATP because there were 2 double bonds. Questions about that? But I will ask you probably one of each. So make sure that you know how to do it. Okay. So I basically talked about those. Odd numbered, unsaturated. Oh, and we did talk about glycerol, but we didn't really go into a lot of detail. I just wanted you to know glycerol feeds into glycolysis, right? And it basically feeds in, you can say the product of step 4 or step 5, however you want to word that yourself. But it's going to be dihydroxyacetone phosphate. That's how it gets fed into. And if you actually were to go through aerobic respiration of that one glycerol, you would get 18.5 ATP. Also, it depends on the shuttle, if you're using a Spartate shuttle. So high end, 18.5 ATP. Okay. Then for fatty acid synthesis, that's going to take place in the cytosol. So again, we're always concerned with location, okay? But if you remember, that's actually up to 16 carbons long. Anything beyond 16 has to be modified in the ER. Okay? And remember, it was the reverse of beta oxidation. Instead, we're going to have steps that are going to be reduction, dehydration, reduction. Okay? And this time our coenzyme is NADPH. NADPH is going to be oxidized to NADP. Okay? And so one of the things we talked about was how much energy is needed to get your fatty acid. And I will ask a question like that on the test as well. So what happens is that all of the carbons that you're going to use to make the fatty acid are going to come from acetyl-CoA. They all originate from acetyl-CoA. But what happens is we need malonyl-CoA. Okay? And so malonyl-CoA, as you convert acetyl-CoA to malonyl-CoA, it takes 1 ATP to do so. Okay? So every time you need to use malonyl-CoA, because every time you add in malonyl-CoA, it adds in 2 more carbons. Okay? So every time you add in malonyl-CoA, it's going to use 1 ATP. But if you remember in the first step, when you first start to make the fatty acid, it's malonyl-CoA coming together with acetyl-CoA. So if I had a fatty acid that was going to be 16 carbons long, and I wanted to figure out how much energy is needed, Okay? What I'm really asking myself is, how many malonyl-CoAs do I need to make this? Because every time I use a malonyl-CoA, I use 1 ATP of energy. So the first thing I want to do then is I want to subtract out 2, because that's from that first acetyl-CoA. We get those 2 carbons from that very first acetyl-CoA that gets added in. Okay? So that leaves me with 14 carbons that I need to add onto this fatty acid. And because every time that I use malonyl-CoA, I get 2 carbons, that tells me that I am using 7 malonyl-CoA. And then for every malonyl-CoA I need 1 ATP. So that also tells me that I need 7 ATP. Another question, if you saw, I think maybe on the practice test, is how many NADPH do I need? Okay, how many NADPH do I need? Well, for that one, it's very simple. Every time I add on malonyl-CoA, there are 2 reduction steps. Both of those reduction steps take NADPH. So if I want to know how many NADPH there are, I just multiply that by 2. So 14 NADPH. Because basically, each malonyl-CoA represents a round. I'm adding in another 2 carbons. And I'm going through another round of fatty acid synthesis. And every round takes 2 NADPH. Okay? So you should know how much energy and how much NADPH it's going to take. You should know, we already mentioned that the reactions evolve. It's going to be reduction, dehydration, reduction. And of course, the sources of carbon. 2 carbons come from acetyl-CoA. All of the rest of the carbons will come from malonyl-CoA, but keep in mind that all of the malonyl-CoA originated from acetyl-CoA. Okay. And then control, and actually citrate is on here, but we didn't actually talk about citrate. I just realized that today we didn't actually talk about citrate, so I'm not going to worry about having that on the exam as well. But hormonal control, it's erased, but we did have hormonal control on there, so you should know glucagon, epinephrine, and insulin and how that controls it. And then we didn't really have time to talk about LDL, so I'm not going to ask you about LDL.
Sorry, but what did you say this was for?
Okay, so when looking at the actual steps and process, 2 come from acetyl-CoA. All of the rest will come from malonyl-CoA. But when you think about it, malonyl-CoA originates from acetyl-CoA. So really, all of the carbons at some point come from acetyl-CoA. And we didn't talk about LDL, so I'm not going to, we didn't go into a lot of detail about LDL, so I'm not going to ask you about that. Yes?
Did you ask on the test about where the carbons come from? And it says.
If I said, where do all the carbons originate from? You would say acetyl-CoA. If I said, otherwise I'd word it, how many malonyl-CoA do you need to make this fatty acid? Then that would be different. Okay, so if I told you you have 16 carbons, how many malonyl-CoA do you need to make this fatty acid? The answer would be 7. But if I said, where do all carbons originate for the fatty acid? The answer would be acetyl-CoA. Okay, so let's go to the practice test. And I'll give you the answers. It's kind of goofy, like I said, I pieced it together, so I noticed I have 2 number 15s. Okay. So even the very first question, it says choose all to apply. I can't ask you to choose all to apply, but I can ask you a very similar question, but you just have to go beyond the E, basically. So it says, what's the following? Oh, we don't need that. I'm just going to do the answers. I don't know what. Number 1 is B and D. B and D. Number 2 is A and D. D is in dog. Number 3 is C. Number 4 is B. Number 5 is D and E. Number 6 is A. Number 7 is C. Number 8 is C and D. D is in dog. Number 9 is B. B is in boy. Number 10 is B as in boy. Number 11 is C. Number 12 is E. Number 13 is B as in boy. Number 14 is D as in dog. Number 15 is B. B as in boy. I had 2 number 15. Oh, sorry, it was 2 level 5. So number 15 was B and D. The first number 15 is B and D. The second number 15 is A. 16 is B as in boy. 17 is B as in boy. And 18 is A. Number 19 is A. Number 20 is B as in boy. Number 21 is B as in boy. Number 22 is A. Number 23 is B as in boy. And number 24 is B as in boy. Now I do want to say something back about this as well. We did write on the board all of turning on and turning off. And I absolutely will be asking questions about that. But as you see on this, another question I can ask is, I can refer directly to an enzyme. So you should know the control enzyme in the process. If you know that glucagon turns off glycolysis, well then you would know that it controls phosphofructokinase, because that's the control enzyme in glycolysis. Okay, so you should know the control enzymes that occur to know how the hormones turn them on and off. Okay? Yes?
Could you go do 20 through 23?
Oh, just tell you the answer? Sure. 20 was B, B as in boy. 21 was B as in boy. 22 was A. 23 was B as in boy. And 24 was B as in boy also. Yes.
Can you repeat 1 and 8?
Sure.
Sorry.
No, that's fine. Number 1 is B and D. B as in boy and D as in dog. And number 8 was C and D. Okay, and really quickly, I think we talked about this before, but I just want to mention it one more time. Your final will be in here. Okay, exam 4 is in the textbook, your final is in here. And you can make up one exam on the final, only one. And you must write that on your scan sheet. But we'll have it since the class will be in here. You can ask your questions that day if you have a question about the exam. What's that? Somebody said 115 and 315 in here.